All right, it looks like we're recording. So welcome to I think it's day 15 of operating systems. This is about where we left off last time. We had talked, we spent most of our day, spent most of our day last Wednesday talking about memory and various tricks that programs can do or that they can do with the help of the operating system to kind of get the most out of the limited physical memory. Until today, we had been planning for contiguous allocation. That is, for a process to run, it needs a big chunk of memory all in one place, all of it kind of occupying a contiguous series of bytes, one byte after another from the start of its memory to the end. A disadvantage of that, what we saw is, I can think of two big disadvantages. One is, it's a little hard to find space for a new program if our memory is externally fragmented. We may have plenty of available space, but it may not be enough to host any one particular program or maybe a big program. And the other reason is, I think the bigger reason that contiguous allocation has disadvantages is it's going to make it hard to do some neat tricks with memory, like sharing memory between arbitrarily many programs. And we want to be able to do that. So we're going to figure out how to do that. And the main contender as a solution for this is page memory. We've done other things in the history of computing, but page memory has kind of emerged as a solution that is good enough for most of the things we might want to do, at least for now. I already introduced this to you. The idea is, and I've got a picture here that maybe illustrates it a little bit. We're talking about some of the stuff on the previous slide. I just wanted to show you this picture to talk about it. So the idea is, we're going to think of a process, or at least with help from the hardware. The OS is going to think of the process as not just being a contiguous chunk of memory, but that contiguous chunk, or that chunk of memory, we're going to think of as being broken into fixed-sized pages. And page size, like I said on the previous slide, is in the neighborhood of ½ kilobyte up to 8 or 16 kilobytes, depending upon the system. I'll go ahead and mention 4 kilobyte pages, so about 4,000 bytes, are really common today as a page size, and a lot of architectures are made to work with that size. So like my picture over here shows, we'll think of a process. Remember, its logical address space is its view of memory. It might think of this first byte of memory, this I, as being in byte 0. And it might think of this last byte of its memory as being in byte 15 or address 15. So we'll think of it as being broken into these fixed size pages. And with help from the hardware, the OS is going to be able to store those pages anywhere it wants in physical memory. To try and do a better job of saying that, we'll think of physical memory as being broken up into little chunks exactly the same size as a page. We'll call them something different when we're talking about physical memory. We call the page-sized pieces of physical memory, we'll call those frames. And you can think of each frame as just the right size to hold a page of a process. When we're storing the pages of a process in physical memory, like my picture shows, they don't have to be contiguous. They don't even have to be in order. I think I said this last time. Maybe we'll store the process's first page 0 might go here, page 1 might go up here, page 2 might go here, and page 3 might go in this frame. What's nice about this technique? Well, if a process's pages don't have to be stored contiguously in physical memory, it gets awfully easy to find room for a new process. If a new process starts up and it just needs 4 pages of memory, all the OS has to do is find 4 available frames, and we can let that process use those frames. We can store its pages in those 4 frames, even if they're not all together in memory. So again, that makes memory allocation a lot easier. I mentioned on my slide, this will get rid of external fragmentation for us. If we're only giving away memory in page-sized pieces, a frame at a time, then any available frame can be in use. So we're not really going to have gaps between processes that we have to worry about. We will pay some internal fragmentation. That's the idea that you may give away more memory than a process needs. Well, imagine I've got a process that doesn't quite need 4 pages of memory. maybe this last page isn't completely full. Well, if I give it a whole frame to store that last page, then there's going to be a little bit of wasted space at the end of the frame. I allocate it to the process, but if it's not using the whole frame, then no one else is going to be able to use the leftover part of that frame. So like it says, we're going to tolerate some internal fragmentation, but allocating memory gets really easy in this model. I'll go ahead and mention this. I wanted to say this a minute or two ago. For my illustrations, for my pictures, and for the examples we're talking about, they are all ridiculously small. I can't fit realistic sized examples on the slide. Here, I'm pretending I've got a process that only needs 4 pages. Well, realistically, a process might need thousands, even millions of pages, depending upon how much memory it needs. So this is a ridiculously small number of pages to make up a process or a realistic process, and the pages are tiny. I said before a page might have, between 512 and 8,192 bytes on it. Here, I just put 4 things on a page. I'm pretending we're working with 4-byte pages, again, because I can fit that on the slide, but keep in mind, realistically, this is a lot bigger. I'm going to back up a slide. I think we already talked about everything here. So a process doesn't have to be allocated contiguously. It's broken up into these fixed size things called pages. In memory, each page is going to be stored in a frame that's exactly the same size as a page. And then we're going to let the process, what we'll talk about next is, we'll let the process believe that its memory is contiguous. Its logical address space, its view of memory, is going to look just like it's 1 byte after another, even across a page boundary like this. With help from the hardware, we can let a process's logical address space look like it's contiguous, even if it's not stored all together in physical memory, even if its physical address space is 1 page stored here and then 1 page stored elsewhere in memory. To do this, to be able to keep up with where each page of a process is stored, we're going to need some kind of a record of that, and we'll call that the page table. The page table just keeps up with, like I said, where each page of a process is stored. It's a table that has a line for every page of the process, and that line, that entry in the page table, says what frame that page is stored in. So it's kind of like an array where every entry of the array is a frame number. So you can think of the first entry of this. So if this is our page table, like I said, it's like an array. This first entry says where page 0 is stored. The next entry, so like the arrow shows, it's stored in this frame of memory. The next entry says where page 1 is stored. It's stored up here. The next entry says where page 2 is stored, and so on. So notice, based on what I just said, it's like an array where the index is page number. If you look up, or if you look at entry 0 of the page table, that's where page 0 lives. If you look at entry 1 of the page table, that's where page 1 lives. So the index into the page table is page number for a process. The contents of that entry is frame number. It says where that page lives. So if we pick one last example, entry number 3, this last one here, says where page 3 lives. And from the arrow, you can see, oh, it lives in this frame here. So the page table is a record built by the OS. And later we'll see it's used by hardware. Instead of using a base and limit register on a modern computer system, this is how the hardware keeps up with what memory a process can access. As it's running a process, it knows where the page table for that process is. And whenever that process tries to access memory, it uses the page table to find where in memory that part of the process's address space lives. Said better, whenever a process tries to access a byte of its memory, whether it's loading an instruction or just accessing data in memory, the hardware automatically says, oh, you're accessing something on, let's say, page number 2 here. The page table says page number 2 lives in this frame of memory. So the hardware, instead of checking base and limit registers, this is what it's going to do on a modern computer system every time a process tries to access memory. This picture, I'm trying to show where each page lives. I'm trying to show the frame where each page lives with these little arrows. But if you were really building this table, it would look more like this. Every entry of the page table says what frame one of the pages lives in. So, we wouldn't really, I would say, I don't know if we can store an arrow in the page table, but we can achieve the same thing by just keeping a frame number. So this 5 up here in the first entry of the page table says where page 0 lives in memory, and this 5 says it lives in frame 5. That's this one right here, and if you count off, there's frame 0, 1, 2, 3, 4, 5. So really what's in the page table is a bunch of frame numbers, and the entry of the page table, or the index into the page table, is for the page number. So I'll say this real fast, page 0 lives in frame 5, page 1 lives in frame 2, page 2 lives in frame 4, and page 3 lives in frame 7. Questions before we move on? We're going to be talking a lot more about page tables. I'm just trying to get the idea across. So this is kind of our first look at how, kind of two things, how memory protection is really done on a modern machine, and overwhelmingly paged memory is what systems use today, and how address translation is done. Remember, we talked about this last time. Address translation is the process of turning a logical address into a physical address. Informally, that's the idea of taking an address that a process sees, the addresses space that processes use, and mapping that to where parts of that process really live in physical memory. Like I said a moment ago, a process can be, you can write your code, processes can run being blissfully unaware that this is happening. They can think of their memory as being one big contiguous address space. So I made a process being kind of happy because it doesn't have to worry about all of this. The OS has to worry about all of this. Like I said, when a new process starts up, it has to find frames to host that process's pages. So it has to find a place to store each of the pages. And it has to build a page table for that process, keeping up with where each of its pages reside. And then it needs, as we'll see in a moment, it needs to tell the hardware about that. It needs to tell the CPU, here's the page table you need to be using. And then as the CPU is running a user mode process, it's using that page table to do address translation. Every time a process accesses part of its memory, and that's very, very frequent, that's happening all the time, the hardware is consulting this page table to figure out where the page that the process is trying to access, where that lives in physical memory. I kind of hinted at this a moment ago. Since every process is using different frames of memory, if you're running 2 processes, each of them would have some frames allocated to them. In my picture, I colored some of the frames kind of greenish, pretend those are for process B, and I colored some of them, same as before, kind of bluish, pretend those are frames holding pages of process A. Each process is going to have its own page table. When I'm running process A, the hardware is going to use this table to figure out where each of its pages live. If I'm running process B, the hardware is going to be using this page table to figure out where each of its pages live. So again, every process is going to have this little table. If you're using page memory, every process is going to have a little table that keeps up with where its pages live, what frames its pages live in memory. I thought we would try some address translation examples ourselves, and I wrote 3 of them down at the bottom of this slide. I guess the point I'm trying to make here is we want to figure out what it takes for the hardware to do address translation, and we want to see that an address really has 2 parts. To do address translation, you have to figure out what frame a particular page lives in, and if every page has multiple bytes on it, then when a process tries to access a byte of its memory, You have to figure out the frame where the page containing that byte lives, and then you have to figure out which byte inside that frame you want. So let's work a couple of examples, and then we'll try to get some takeaways from that. So let's pretend, like this first example, process A tries to access byte number 3 of its address space. We're counting from 0. So byte number 0, 1, 2, and 3 must live on the first page. In this example, we're pretending the page size is 4 bytes, kind of like my picture shows. Again, that's ridiculously small, but we're pretending every page is 4 bytes. So if process A accesses byte number 3, well, byte number 0, number 1, number 2, and number 3 all live on its first page. So if we look at process A's page table, well, that page lives in frame 5. That's this frame right here, frame number 5. If it's accessing byte number 3, well, that's the last byte on its first page. We can just count that off. Byte number 0, byte number 1, number 2, and number 3 all live on the first page. So byte number 3 must be this I right here, the I at the last byte stored in frame 5. I deliberately picked a simple example for that. I picked one that was on the first page, which maybe made it easier to think about. My next example, pretend process B tries to access byte number 8 of its address space. Well, we can count that off. If process B tries to access byte number 8, well, byte number 0, 1, 2, and 3 are on its first page. Byte number 4, 5, 6, and 7 are on its next page, so page number 1. Byte number 8 would be the first byte on its third page, or counting from 0, on page number 2. So if I look at its page table, that line tells me where page 0 lives in frame 9. I don't care about that. Page 1 lives in frame 3. Page 2, that's the page we care about. Again, I'll count this off quickly. Bytes 0, 1, 2, and 3 live in frame 9. Bytes 4, 5, 6, and 7 live in frame 3, but I wanted byte 8. So that lives in frame 6. That's where page number 2 is stored. Here's frame 6 right here. Byte number 8 would be the first byte on that page. So if I look in frame 6, that's this E right here. And again, byte number 0, 1, 2, and 3 live in page 1. Byte 4, 5, 6, and 7 live in page 2. Byte 8, 9, 10, and 11 live in page 3. From the page table, we can see that's stored in frame 6. And byte 8, just like I counted off, must be this E here. It's the first thing stored on page 2, and that's in frame number 6 according to the page table, so that's this E right here. I picked one more example, and I deliberately made this one a little bit bigger, so instead of counting on our fingers like I'm doing here, we can think about how this must actually work. Whenever we try to access a byte of memory, we need to figure out what page that byte lives on. And instead of counting off, we could just do a division. If every page is 4 bytes in size, if you give me an address like 14, I can divide by the page size, I can divide by 4, and that'll tell me what page it lives on. And 14 divided by the page size, divided by 4, well, if you divide and truncate, that gives you 3. So 14 divided by 4, divided by the page size is 3. So that says this byte number 14 must live on page 3 of process A. We can look up at its page table, and this last entry, entry number 3, says the page you want lives in frame 7. So that right there in frame 7, that's the page I want. Which byte of that page do I want? Well, there are 4 bytes. In this example, there are 4 bytes on each page. I divided by the page size. I divided the address by the page size to figure out which page I wanted. If I mod by the page size, that'll give me the remainder, and that'll tell me which byte I want on that page. If I take 14 and mod it by 4, mod it by the page size, that gives me a remainder of 2. So that says, well, within your last page, which is stored right here in frame 7, you want byte number 2. And you could count that off on your fingers if you want to check and make sure that works out. But as the examples get bigger, we're going to want to depend on math to solve this for us rather than just counting it off a byte at a time. So in frame 7, that's the page we want. We wanted byte number 2 in that page. Well, that L is byte 0, that I is byte 1 on this page. That T is byte 2. So byte number 14 of process A must be that T right there. It's the second, or byte number 2 on page 3 of that process. Here, I think we were just trying to kind of intuitively figure out how paged memory must work. This is what we figured out. I tried to say the stuff that was on this slide as I was talking through it. If a process has a page table and it tries to access some address in its address space, well, it's accessing a logical address because that's the only addresses a process ever knows about. And what we were just doing was we were trying to intuitively work out how address translation must work in page memory. Let's pretend A sub L is the logical address a process is trying to access, and address translation has to convert that to a physical address. We'll call that A sub P, and that's just the address where the byte that the process is trying to access, where it really lives in physical memory. So with page memory, to convert a logical address, we're calling it A sub L, to a physical address A sub P, what did we just do? Well, first we said, I got to figure out what page a process is trying to access. And we decided if we take the logical address and divide, divide by the page size, that'll give us the page number, which page the process is trying to access. We'll call that P. In our last example, that was page number 3. And we also said, well, within that page, there are a bunch of bytes. Realistically, maybe 1,000 or 8,000 bytes. So of all those bytes, we need to figure out which one the process is trying to access. We'll call that the offset. That's kind of how far into the page is the process trying to access. And we just saw that's the remainder. If dividing by the page size, if dividing the logical address by the page size gives us the page number, modding by the page size gives us the offset. It tells us which byte within the page do you want. So now we know P, which page we need. We know which byte within that page we want. That's the offset. We have to go figure out the frame where that page lives. And that's what the page table stores. If we go to the page table and look at index P, that tells us what frame page P lives in. So we'll call that F, the frame number. And then from that, we just need to compute a physical address. Well, if you know the frame number, F, if you want to know where that frame starts in physical memory, like if you let me back up, this first frame starts at byte number 0 in physical memory. This next frame would start at byte number 4, just counting by 4s here. The next frame would start at byte number 8. The next one would start at byte number 12. So if you want to know, if you have a frame number and you want to know where that frame starts in memory, that's just going to be the frame number times the page size, kind of like we were just doing. But you don't necessarily want the first byte within that page. We just said a page could have more than 1,000 bytes on it. You computed the offset to figure out, well, within that page, which byte do you want? We call that the offset D. If we just add that to the start of the page, that tells us the physical address for the byte the process is trying to access. Given a logical address, A sub L, which is what we started with, this little procedure converts it to a physical address. Where does that address really live in physical memory? Questions before we move on? We're about to make this process a lot more efficient. All right, I'm not hearing any questions. So one thing to notice is the way I've described this process here, it seems ridiculously expensive. The way I described it, whenever a process tries to access memory, and again, this is, hundreds of millions of times a second, maybe more often. I'm describing a process where you have to take an address, you have to do a division operation, you have to do a mod operation, you have to do a table lookup to look in the page table, and then you have to do a multiply and an add just to get the physical address. And all those operations, if you had to do that on every memory access, it would slow down your computer system by a factor of 20 or more. So we can't really afford to do this, at least not the way I've described it. But there is one obvious trick that is going to make this computationally cheap. And we already know it, we just haven't talked about it. In practice, your page size is always going to be a power of 2. And the reason that matters is because most of these mathematical operations become cheap when the page size is a power of 2. For instance, and this slide is really just a copy of our previous slide. I'm just trying to illustrate how these operations get cheap as long as your page size is power of 2. Let's pretend your page size is 2 to the n words. So if your page size was 1 kilobyte, that would be 2 to the 10th words, or 2 to the 10th bytes. If your page size was 4 kilobytes, that would be 2 to the 12th words. Let's pretend let's pretend your logical address space is 2 to the m words. So where m is going to be larger than n. So if your logical address space was 32 bits, was 4 gigabytes, then that would be 2 to the 32 addresses, 2 to the 32 bytes of memory. So as long as that's true, like I said, like I tried to say, most of these operations get really cheap. Dividing by the page size, well, if you're dividing by a power of 2, that's really just a bit shift operation. Or said differently, dividing by 2 to the n is really just the high order bits, everything except the n low order bits. And I say that better in my slide. If your address is m bits in size and the page size is 2 to the n bits, then the page number is just logical address throwing away the bottom, the low order n bits. So keeping everything else, keeping m minus n bits of a logical address. I like that because hardware can do that cheaply. If you give it a logical address, it can just go get the m minus n high order bits and ignore the rest. Same kind of thing with the mod operation. If your page size is a power of 2, modding by a power of 2 is just throwing away the high order bits and keeping just the n low order bits. And again, hardware can do that pretty much for free. It can take a logical address and just grab the low order n bits of it. So these two operations just got really cheap. Looking up in the page table, that's still going to cost us something. The page table is like a big array. So looking up page number P, even if it was cheap to get page number P, looking that up in a big table, it's not like we have to go through the whole table, but we have to find entry number P of the table and see what's in that. So that's like looking into an array, and that's going to cost a memory access. So this part's probably the most expensive right now. And then once we have a frame number, gluing that together with the offset gets cheap because I don't really have to do a multiply. Multiplying by a power of 2 is just another bit shift operation, or you can think of that as taking the frame number and writing that into the high order bits. For the low order n bits, you can just take the offset and put that in the low order n bits. And again, hardware can build that physical address pretty much for free. It can just take the entry out of the page table, put that into the high order bits, everything except the n low order bits. And then for the n low order bits, it can just use the offset for that. I don't know if you need this picture. Years ago, I found that students had a hard time visualizing how logical addresses work. And in this previous slide, we're kind of warming up to the idea that if you take a logical address, and if your page size is a power of 2, and it's pretty much always going to be a power of 2, at least for realistic examples, you can kind of think of that address as consisting of 2 parts. A bunch of high order bits that give you the page number, and a bunch of low order bits that give you the offset. To try to illustrate this, I showed what addresses would look like on a computer system with a 32-bit logical address. And that's, we're not generally using computers with address spaces that small anymore, but otherwise I don't know if I could fit it on my slide. So we're pretending we've got a 32-bit logical address. If you count all these bits, there should be 32 of them. We're pretending that the page size is 4 kilobytes, so 4,096 bytes. That's 2 to the 12th bytes. So I colored the low order 12 bits in green. And I want to show that as you go through the address space, you really can think of these low order 12 bits as offset. That's which byte on the page you want. And the high order, I guess we'd have 20 high order bits left in this example. The high order 20 bits are page number. Well, if you looked at the first address of logical address space, it would be address number 0 in binary. That's just a bunch of zeros. And if your process was broken up into 4 kilobyte pages, well, that'd be the first address on page number 0. If you incremented the logical address, that'd be the next address on page number 0. And if you kept doing that, when you got to the last address on page number 0, it would look like this. It would have all ones in these low order 12 bits, and it would still have all zeros in the high order 20 bits. This would be the last address on page number 0. And if you did this trick that we're talking about, well, the page number would still be 0. So that's still something on page number 0, but the offset would be as big as it could be. As a number, it would be 4,095, the last byte on page number 0. If you incremented that, well, then all these ones are going to wrap around to zeros, and you're going to get a high order 1 in the next bit. This would be the first byte on the next page, on page number 1. And sure enough, if you look at these purple bits, you're on page number 1. If you look at the green bits, the low order 12 bits, you're on byte number 0 of page number 1. If you kept counting up from there, you'd go through all the addresses on page number 1 until you got to the last one. Same as before, that'd be address number 4,095, the last address on page number 1. And then if you added 1 to that, you'd be on the first address, address number 0 on page number 2. And if you kept doing that, the same thing would be happening. Once you finally got to the second to last page, its page number would look like this. The last byte on that page, the offset would look like this, all ones. And if you added 1 to that, you'd wrap around again to byte number 0, the first byte on the last page of your logical address space. Again, I don't know if you need this picture. I don't know if you need that kind of explanation, but if that helps you look at an address and say, hopefully, oh yeah, if you made sure the page size was a power of 2, you could think of that address as consisting of 2 parts. Low order bits that give you offset, which byte on a page do you want? And high order bits that tell you the page number, which page of a process's address space do you want? And from now on, that's what we're going to be doing. Hopefully that makes sense to you. We're going to be thinking of a logical address as consisting of 2 fields. If the page size is 2 to the n addresses, in the previous example, we were pretending that's 2 to the 12th addresses, 4,096 addresses. Then the low order n bits we'll think of as offset, and everything else, all the remaining high order bits, we'll think of that as page number. The job of address translation is to take an address that we think of as 2 fields like this. From the page number, we're going to figure out where that page lives in memory, what frame it lives in. That'll be the frame number. The address translation hardware, the CPU, will stick that frame number in the high order bits. And in the n low order bits, it'll put the offset, which it just copied from the logical address. If you wanted byte number 5 of some page, Once you figure out the frame where that page lives, you still want byte number 5 within that frame. The frame number you got from looking that up in the page table. Here's a picture out of your book that shows what we've been talking about, and it's what I just talked through. I'll try and say it real fast. Every time, if you're running in user mode, every time a process tries to access an address, the hardware will take that address, break it into 2 fields. The offset, the low order bits, the offset, it'll hang on to the page number. It'll go look at line P of the page table. That'll tell it what frame where that page lives. It'll take that frame number, write it into the high order bits of the physical address. And for the low order bits, and when I say low order bits, I mean based on how large your page size is. If your page size is 2 to the n addresses, if it's 2 to the n bytes, then it's the low order n bits. So it'll put the low order n bits, it'll just copy that from the original logical address, and that tells it where, that tells the hardware where to go in physical memory. That gives us the physical address that this logical address maps to. Questions before we move on? So what I think I've told you is kind of how page memory works. And like I said, modern hardware, this is the prevailing mechanism for figuring out where to store processes in memory. We don't have to find one big contiguous chunk. And we can, if we do this trick, we can do a lot of other fancy tricks that we're about to try to talk about. Let's work one example, and it's kind of the example that I showed in that figure where I was showing all the numbers in binary. And this is kind of representative of how a 32-bit logical address was paged, at least around the late 90s and early 2000s. If you had a logical address that was 32 bits, it was common on Intel style hardware to have a 4 kilobyte page size. So that's 2 to the 12th bytes. The reason I say that 2 to the 12th is that 12 tells us in a logical address which bits are the offset. So if you've got a 32-bit logical address, that means the low order 12 bits, those are offset. Those just tell you which byte in a page you're trying to access. And everything else, in this case, the remaining 20 high order bits, those would be page number. So a logical address on this system would look like this, 32 bits altogether. The high order 20 bits give us the page number. The low order 12 bits are the offset. They tell us which byte we want within that page. On a system like this, how big would your page table have to be? Well, we can almost read it off of this. If your page number is 20 bits, well, and then how many different pages could a process ask for? Well, it's got 20 bits that it can use to specify a page number, or if you think about all possible values that could show up in these high order 20 bits, that's 2 to the 20th different page numbers that could show up in a logical address. So that would mean a page table for this kind of address space would need 2 to the 20th entries, one element, one entry for every possible page number. And 2 to the 20th is about 1 million. It's a little more than 1 million. So on a system like this, every process is going to have its own page table, or at least the OS is going to build a page table for every process. And that table is going to be pretty big. It's going to have, like I said, about 1 million entries to it. Where are we going to store that page table? Well, if it's got 1 million entries in it, we probably can't afford to keep it right on the CPU. It's going to be a big table. To store a bunch of big tables like that, again, tables with about 1 million entries in them, we're going to have to store those in main memory. So in practice, when a process is running, it's got a page table that's stored in main memory along with all the code for that process and along with all the data that process is using. If the page table is stored in main memory, then every time we start running a process, the OS is going to have to tell the hardware where the current page table lives. Again, every process has its own page table. So when the OS context switches, when it lets a process run for a little bit, it needs to plug in the page table for that process, if every process has its own page table. So to do this, we're going to count on our hardware having a page table base register. That's a special purpose register, just like any other, well, just like other processor registers. But the job of this one is to keep up with the location, the starting location of the page table. If a process, like I said, if the OS context switches between process A and process B, its to-do list for that is going to include update the page table base register so it points to the start of process B's page table. And then when we go back to running process A, we're going to update the PTBR, the page table base register again. So this is one more thing the OS has to do when it context switches. But we get to save base and limit registers, or I mean, we don't need to do that anymore, because if we're using paged memory to do address translation, it's also going to do memory protection for us. If we've got paged memory, we don't need a base and limit register anymore, because the page table is going to be doing that job. To try to explain that, well, the purpose of base and limit registers was to make sure a process couldn't access memory that didn't belong to it. If we've got paged memory and we've got a region of memory that the process can access and then other regions it shouldn't, if we want to prevent it from accessing stuff it shouldn't, we just don't put entries in the page table for that. If a process, if every memory access that it tries to do, if that goes through the page table, if that gets address translated using the page table, then any memory that a process shouldn't access, we just don't put a page table entry for that. And that'll be our new way of keeping processes out of memory that they shouldn't access. Questions before we move on?
Yes. Can
Good,
we
go
give
ahead.
a process different permissions for each page, like so that it could only read a library or something?
Yes, we're going to talk about that later. That is a good question. I'll go ahead and give you a preview, and that is, so far I've been pretending that every entry of the page table just has a frame number, but pretty soon we're going to realize, oh, it'd be handy to put a few other things in every entry to control access to memory. And we'll start doing that. I'm looking ahead. I think we'll get to that today, but you're right that we could get a lot more value out of page table entries. And that is going to be the real answer for how things like read-only memory are implemented. Good question. Other questions? Thanks for the questions. Like I've said before, it lets me know I'm not alone here. All right, so we're going to sneak up on that idea we were just talking about, and we're going to think about how to store a page table. I just want to think about the number of bits that are going to be required here. Let's pretend we had a system that had a same example we were working before. It had a 32-bit logical address and a 4 kilobyte page size. So that would mean a logical address, we could think of it as consisting of these two fields, page number and offset. I added the idea of, let's pretend physical memory is also 32 bits. So that would mean if you looked at main memory, it's got about 4 billion different addresses you can access. That's 2 to the 32 is a little more than 4 billion. So if you think of an entry of the page table, we said that needs to tell you which frame a particular page is mapped to. But if your memory is only 2 to the 32 bytes, and it's broken up into fixed sized frames, each of them 4 kilobytes in size, then how many frames could you have in memory? Well, that's just a division problem. We said you've got two, I'm going to try this at some risk. I got this new pen tablet, and normally I'd be writing this kind of thing on the board. I'm not sure if this is going to work, but I was planning to use it later. I was up here, I'll scribble in the corner. We said your total memory is 2 to the 32 bytes of physical memory. But we're going to think of that as we're going to allocate that a frame at a time. So every frame, we just said, was 2 to the 12th, 4 kilobytes, so that's 2 to the 12th bytes. So how many frames in your 2 to the 32 sized memory, in your 4 gigabytes of memory, if you had 4 kilobyte sized pages, how many frames could you have? Well, that's total size of the memory divided by size of a frame, 2 to the 12th. And that is, well, 2 to the 32, total size of your physical memory, divided by a size of a frame, that's just 2 to the 20th. So, even though your memory has 4 gigabytes, you've only got room in that physical memory for 2 to the 20th frames, about 1 million frames. For specifying the frame number, how many bits do you need? Well, if you've got 2 to the 20th frames, you need 20 bits to specify the frame number. That would let you give the frame number for every possible frame in memory. How many bits do you think you should use for storing the page table? Well, we just said you need at least 20 bits just to give the frame number. 20 bits doesn't divide evenly by bytes. You could use 3 bytes to store each entry of the page table, and that would give you 24 bits. So that's enough to store these 20 bits with 4 more bits to spare. In practice, you probably wouldn't do that. That's a bad idea. Because if you made the page table an array with 3 bytes per entry, it's a little hard to look up stuff in that array, especially if you have to do this really fast. It is cheaper to index into an array where every element is a power of 2 in size. So in practice, even though, we could have 3 bytes, which would give us 24 bits. That's probably a bad idea, like I said, because it's computationally expensive to index into an array like that. But if we spent 4 bytes per page table entry, that would give us 32 bytes, which is still plenty to store the 20-bit, sorry, I said that wrong. I'm going to re-say these. I worry that I said bytes when I was pointing over here. So if we spent 3 bytes per page table entry, that gives us 24 bits. But that's hard to index into. If we spent 4 bytes per page table entry, well, now we got plenty of bits. And this one, we spent 4 bytes per page table entry, that gives us 32 bits. Now we got plenty. And this one's computationally cheap to index into. Sorry if I got bits and bytes confused a couple of times there, or at least said the wrong words. So in practice, computer systems are always going to use a page table where every entry is a power of 2. And in practice, the size of a page table entry is usually going to be the same size as a pointer. You can think of a page table entry as pointing to the start of a frame in memory. And it's going to be allocated, not always, but most of the time, using the same size as, same number of bytes it takes to store a pointer. So on a 32-bit machine, 4 bytes to store a pointer, that gives us 32 bits. On a more modern machine with 64 bits, probably 8 bytes per page table entry. And just to simplify things, we're going to assume that for the rest of the semester, that the size of a page table entry is the same as the size of a pointer. The thing to observe is, and this is, I wanted us to be able to think about this, but I wanted to observe, we only need 20 bits per page table entry, just to say the frame number. If we got 32 bits, then we got some extra bits we could do stuff with. We're going to count on that. In practice, the way the page table is stored, you've got more bits than you need just to store the frame number. Backing up, back here we said we only need 20 bits. But look, in practice, we're probably going to have 32. So let's do something with the extra bits. And with the help of hardware, some of those extra bits in each page table entry are used to get more value out of the page table. The first most common thing is one of those bits is used as a valid bit, or a valid invalid bit, you might call it. That's going to be used to mark page table entries as valid or invalid. What does that mean? If the page table entry is marked as, and I've got a picture for this. Here, we're going to pretend a page table looks like this little table here. Every entry of the page table is going to have a frame number. We've already said we've got to have that. Every page table entry is going to use one of these extra bits to keep up with whether that entry is valid or not. Valid entries will pretend if they're marked, if the valid bit is true, if it's on, then that entry is valid. If it's off, if it's 0, like this entry, we'll pretend it's invalid. If you try to access an invalid page, the hardware won't let you do that. If you try to access a valid page, the hardware will address translate that for you. So you can think of the valid invalid bit as marking parts of the process's logical address space that it can and cannot access. In this example, if a process tries to access something on page 0 or page 1, those are marked valid. So the process will be permitted to access these frames of memory. But this page, page number 2 for the process, is marked invalid. In which case, if the process tried to access anything on that page of its memory, the hardware would catch that, and I'll go ahead and say it would trap to the OS, just like any other error. That would be the process trying to access something in its memory that it's not supposed to access. The OS can fill in the valid and invalid bit to indicate to the hardware, here's parts of a process's memory that it's okay to access, here's parts that if it tries to access, you need to let me know about that. Why would you want to do this? Well, if you had a process that didn't need nearly the maximum number of pages, maybe it just needed a little bit of memory, you could use this valid invalid bit to mark all the stuff in its memory space that it didn't even need, that wasn't mapped to anything in physical memory. Especially for a new process, you could use this to build a new process that had just a little bit of memory. And then as it started running, as it needed more memory space, as it called malloc and allocated more space, as it started using more stack space, you could use these valid invalid bits to let the process grow as it ran. You might have a lot of entries of the page table that started out invalid, but then as the process needed more memory, the OS can go in and fill those in so that they point to something. Here's a picture that I made trying to show how you can think about this. It's not to scale, because on a modern, so pretend all of these little boxes are pages of a process's address space. The ones that I've colored in, think of those as pages that the process is using right now. Like maybe your code is in these purple pages, maybe you've got a shared library in these green pages, maybe your heap space is these yellow pages, and maybe your stack is these red pages. Pretend all the white pages are ones that are currently marked invalid. If a process tries to access those, it's going to trap to the OS. Those are parts of the process that it shouldn't access yet. But the OS can allocate space for the process so that there's plenty of room for it to grow later. Maybe when it starts up, this huge expanse of pages are all marked invalid because the process doesn't need those yet. But as it allocates more and more heap space, the OS can graft new pages, new frames into these page table entries so that the process can access them. And this is how processes are implemented. Think of your logical address space as being this huge expanse of potential addresses. And on a 64-bit machine, it really is a lot like that. There's a lot of room for your process to grow. Initially, all those, or many of those entries might be marked as invalid. Your process doesn't have any business accessing that. But as your process runs, it has room to grow. I've got an example program. I think we'll look at it a little bit later instead of right now, but it shows this. It shows that if you look at the addresses of your heap space and your stack space, those addresses are on a modern computer system. They are so far apart that your program couldn't possibly have access to all the memory in between those. because in practice, your computer doesn't even have that much memory, at least on a 64-bit machine. But you can think of that as the OS leaving plenty of space for your program to grow into later. Questions before we move on? All right, so I made the point a couple of slides ago that in practice, your process starts out with, in practice, your page table entries have some extra bits beyond the ones you need just for a frame number. We just said we're going to spend one of the, or with help from the hardware, one of those bits is going to be used as a valid invalid bit. I listed some other common things that we're going to assume for processes. On modern hardware, it's common to use a bit as a read-only bit. We kind of had a question about this later. Pages can be marked as read-writable. If this bit is 0, we'll assume a process can read and write to that page. Or it could be marked as read-only. That means the process can look at what's on that page, but if it tries to modify it, the hardware will trap to the OS. So we're going to assume we have a bit for that. It's common for hardware to have a modified bit. This is sometimes called a dirty bit. It records, well, these first two, you can think of those as being set by the OS, and then the hardware uses those bits to know what it should permit a process to do. The next two bits are kind of the other way around. These are set by hardware, and the OS can look at them to figure out what's going on in a page. The modified bit, whenever a process writes to a page, writes to any byte on that page, the modified bits get set, and that lets the OS tell if a page has been written to or not. It's not exactly the same idea as the read-only bit, but this is a way the OS can tell if a process is just looking at a page, or is it writing to that page? Has it modified it? Reference bit is kind of like the modified bit, but it gets set whenever a process reads or writes to a page. So we could think of this as a way for the OS to tell if a page is being used or not. If this bit is clear, it means the process has never used that page. If it's set to 1, it means the process has either read or written that page. It's also common for hardware to support a no execute bit. Normally, any page can contain code, and the CPU will happily run code that's on that page. But if you set the no execute bit, the hardware will refuse to run code that's stored on that page. And this is really a security measure. You've probably seen in C class, and we'll see this again later, that certain attacks, buffer overflow attacks, might attempt to write executable code into a process's stack and then trick the process into running that code. And this used to be a pretty common type of attack. This is a countermeasure against that. A process can have its stack space set as no execute. And then even if you have a buffer overflow, which could still be exploited, it can't be exploited as easily because you can't write code into the stack space and then trick the program into running that same code, at least as long as the no execute bit is set. So we've talked about what a page table might look like. Here I listed what a page table might look at. I wrote down 4 of the bits we just talked about. I left out the no execute, but this is a page table for a ridiculously small process. This page table has 8 entries in it. And for each entry, I'm saying pretend we've got a frame number, we've got a valid invalid bit, we've got a read-only bit like we just talked about, we've got a modified bit, and we've got a reference bit. These first 2 get used by the hardware. These next 2, like we just said, get set by the hardware. Let's pretend logical addresses are 8 bits in size, which is ridiculously small, but it gives us an example we can work through. Let's pretend a page is 32 bytes. And again, that's ridiculously small. We said a page is probably going to be in the neighborhood of a few thousand bytes. But for a small example, a page here, we're pretending it's 32 bytes. If a page is 32 bytes, I'll write it down, that's 2 to the 5th bytes. The reason I write that, because 2 to the 5th is 32. And the reason I write that down is knowing the power of 2 here is going to help us make sense of these addresses. So, and I think I said this, we're pretending a logical address is 8 bits. So here we're pretending a process tries to read from this logical address and then it tries to write to this other logical address. I wanted to do address translation using these examples. So let's work through these 4 examples, and probably I'll put together a quiz for you after this where you get to do the kind of thing we're doing here. If this is a logical address, we've said, well, you can think of a logical address as consisting of 2 parts, a page number and an offset within that page. Which bits of this address are which? I'll give you a moment to think about it. And then I'll say, well, we kind of figured that out up here. We said if page size is 32 addresses, if a page is 32 bytes, that's 2 to the 5th bits to specify any byte within a page. So 32 is 2 to the 5th. So that means within an address, the offset must be the bottom 5 bits, the low order 5 bits. So I'm going to draw a little line here to remind me, well, these low order 5 bits would let us specify any location in a 32-byte page. So everything else, these high order 3 bits, must be page number. So if I had to address translate this read from this particular address, I can see, oh, that's a read from page 010 in binary, or in human, that's just 2. So I'm reading from page number 2. I'm trying to read this byte on page number 2. Well, if we're going to do address translation, we take the page number, we go to our page table and say, what can you tell me about page number 2? Well, counting from 0, this first line tells me about page 0. This next line tells me about page 1. This is page number 2. Well, here's the frame it lives into, but I don't really care about that because of this 0 here. That page is invalid. So it means you can't access that page. If a process tried to do that with this page table, it wouldn't be permitted to, or at least we would trap to the OS and the OS would decide what to do with that process. So we're going to stop address translation there because it wouldn't be permitted for this page. Questions about that example? We got 3 more. All right, continuing. This next example, same thing. Since the page size is 32 bytes, then the low order 5 bits must be offset, and everything else must be page number. So that write to page number 111, that's binary for 7. So that's this last entry in the page table. Now that one is valid, but it's marked as read only, and we're trying to write to it up here. So same as before, this would not be permitted by the hardware. If you tried to write to a page that's marked read only, that would trap to the OS, and the OS might not kill you. We'll talk about some exceptions in a moment, but it wouldn't let you write to that page, at least not without deciding what to do. So this one also doesn't translate. But I bet the next 2 will, because we need some that we have to do something with. So this read from this logical address, same here, the low order 5 bits must be offset. I'm trying to read from page 1. If I look at line 1 of the page table, that's line 0, so this is line 1. Well, that page is valid, you can access it. It's read only, but you're only trying to read from it, so that's okay. It lives at frame 00101. So this will translate. This will translate into, remember, for the frame, for writing down the physical address, the frame number goes into the higher bits. So I'm just copying the frame number from over here, 0, 0, 1, 0, 1. And then the low order bits are just the offset. Which byte in that frame do you want to access? And copying the offset, that's 0, 1, 1, 1, 0. I'm just copying these 5 low order bits here. So this read would be permitted. This is where the hardware would go in physical memory when you try to access that, at least according to this page table. You just read from that page. So you didn't modify it, but you did access it. So if previously That was not referenced. I'll just scribble this out. Now the reference bit gets set to 1. The hardware does that automatically to help the OS see what's been referenced and what hasn't. We got one more example. Our last one, you're trying to write to page 4. I'm just converting that binary into a 4. Well, there's there's page 0, 1, 2, 3, 4. So that's this entry right here tells us about that page. It's valid, which is good. It's not read-only, so you're permitted to write to it. We'll go ahead and say, well, if you're going to write to it, this modified bit is going to get set by the hardware, and the reference bit's going to get set because you accessed it, and you wrote to it. So those bits will both get changed. This will translate into, well, the high order bits come from the frame number. So that, according to this example, that's 11011. That's the frame where that page lives. And then the frame has 32 bytes in it. Which one do you want? These 5 bits tell us. 1, 0, 0, 1, 1. So these last 2 examples translate as I've shown here. And I went ahead and tried to show how these other bits are going to get used and updated. One thing to notice about this is the logical and physical address spaces may be different sizes. We started with 8-bit addresses over here, but when we translated them, we ended up with 10-bit addresses. That's because over here in the page table, the frame number had 5 bits in it. So here we've got this illustrates a computer system where the physical address could be a lot larger than the logical address. What would that mean? It means that you have more physical memory. You might have more RAM than any one process could use. If a process, and again, these are ridiculously small examples, but if a logical address is only 8 bits here, that would mean a process can only access 256 different bytes of memory. That's all you can get to with 8 bits of address. But our physical address is 10 bits in size, meaning you've got 1024 bytes of memory. It's just no one process could use all of that. And this could make sense. It might mean you could have a computer system that could have enough memory to run, in this case, 4 processes, giving each of them the maximum amount of memory. It's just no one process on this system could use all that memory all at once. Our computer systems today with 64-bit logical addresses, they're kind of the other way around. A process might be running and it might be using 64-bit addresses, but no realistic computer system could actually have that much memory. No system, you could never run at least not right now, I'll say not any time in the near future, are you going to be able to run a process that could really use 2 to the 64 bytes of memory. So processes have way bigger logical addresses than a realistic physical address space. That's also useful, and we kind of talked about that a few slides ago. It means I can give a process a logical address space with lots of gaps in it, with lots of room for that process to grow. And even if I don't know where it's going to need to grow, I can space out the regions of its memory with lots of room in between that maybe initially isn't marked valid, but then as the process starts needing more memory in certain regions, the OS can structure its address space so there's plenty of room to grow. Questions before we move on? We got about 6 minutes left. I think we can probably cover one more topic. All right, moving on. I've kind of hinted at this. I said when a process tries to do something sneaky with its memory, like if it tries to modify a read-only page, or if it tries to access an invalid page, well, the hardware is going to trap to the OS, and the OS might kill the process. It might say, oh, you're a bad process. You're trying to do something that I didn't want you to do, so I'll terminate you. But there are some cases where the OS can do something more useful than that. I've called these paged memory tricks. These are things you can do using paged memory that let processes get a lot more out of memory. I've listed 3 here, and we've kind of talked about one already. Paged memory lets us build in room for a process to grow. And I've had a picture that tried to show this. You can think of your logical address space as being this vast space of potential memory addresses you could access, but that is sparsely populated. So you might have a little region of memory here that you can access, a little region of memory elsewhere, and a huge region of memory in between that is all marked as invalid. Think of that as room for the process to grow. By building big regions of memory, or big gaps between regions of memory, we leave plenty of space to graft in pages in the future. And the OS could do this with your stack. If your stack starts out needing just a little bit of stack space, but then you start calling some subroutines and they need some additional memory on the end of your stack, and then you start calling deeply nested subroutines and they need even more memory. If the OS catches you using memory right off the end of your stack, it could say, oh, I bet you're trying not to, or sorry, you're not trying to do anything sneaky. You just need a little more stack space. Let me go get that for you. It can find some available frames and graft them into your stack space and let you resume running with a slightly larger stack. And then if you exceed that space up to a limit, it can graft in additional pages. Initially, it can start out with a small stack and automatically grow your stack as you you can think of it as bumping the end of your stack. You do hit an invalid page, you do trap to the OS, but instead of killing you, the OS could give you a little bit more stack space. So that's kind of this first bullet item. The next one is shared memory. And this is kind of where I claim this is the main reason we got into paged memory. We said, if processes have to have contiguously allocated memory, it's going to be hard for them to share memory, at least in a particularly useful or flexible way. Paged memory will let processes share any memory they want up to a multiple of a page size. So they can't share just 1 byte of memory, but they can share any number of whole pages if they want to, at least with help from the OS. That's what I've tried to illustrate here. For processes to share memory, again, they have to make system calls. You've seen the system calls. You've written code that shares memory. When you make those system calls and say, I want to access a chunk of shared memory, the OS will build your page table, or it will modify it so that certain entries of your page table might map to the same memory as other processes' page tables. Here, I built 2 page tables for process A and B. For process A, its first page is stored in frame 2, and if you look at the picture, you can see, well, no one else is using frame 2. Same thing, its last page is stored in frame 5, and no one else is using frame 5. So that's memory just being used by process A. Same kind of thing for process B. Its first and last pages are only owned by it. But these 2 middle pages, if you look at the page table for A, it says my page number 1 and 2 are stored in frame 3 and 6, and the same thing for process B. Well, the middle region of their memory maps to the same frames of physical memory. Anything that process A writes into this purple frame here, process B is automatically going to see that in its memory because it maps to the same frame. They're both storing page number 1 of their address space in that same region of memory. These page tables are tiny, but imagine that you had a page table with 1 million or more entries. You could have big sections of pages that were private to your process, and you could have other big sections elsewhere in your page table where you had asked the OS to let you share memory. When you run 2 different copies, even if you didn't ask for this, if you run 2 different copies of the same program, the OS will do this automatically for those 2 programs. It'll say, well, if 2 processes are running the same program, they don't really need 2 different copies of the executable code for that program. I can let them share that, but I'll mark it as read-only using that bit that we talked about a moment ago. Any shared code between those 2 programs, they can both use 1 copy of that code, so that'll save us some physical memory. But I'll mark it as read-only so that if one of them tries to be sneaky and modify that code, they won't be able to do it. They won't be able to damage the other program by modifying shared code that they're both running. And that's secretly why, if you remember from C class, why literal strings aren't modifiable. Just like code, the compiler usually writes literal strings into the text section of your program, which means they might be used by multiple running copies of your program, which means the OS can't let you modify them. Looking at the clock, I've used up all my time for today. We've got one more page memory trick, but we'll save that for next time. Thanks for your attention. I'll see you on Wednesday. I'll go ahead and stop recording, and if you have questions, hang around and I'll try and take those.